Hi, welcome back to Technical Mathematics lectures conducted by Vadhyar Online Academy. In the previous lecture, we discussed about limit of a function. In lecture 20, we will discuss about continuity of a function at a given point. So let's get started. Let's see continuity of a function at a given point. A function f of x is said to be continuous at a point x equal to a if limit x tends to a, f of x is equal to f of a. So for a function to be continuous at a point x equal to a, it has to satisfy this condition, that is, limit of the function at that point should be equal to f of a, that is, value of the function at the point x equal to a. So when you substitute x equal to a in the function, we will get the value of f of a, that is the value of the function at the point x equal to a. This must be equal to the limit value existing at the point x equal to a for the function f of x. So if this condition is satisfied, we may say that the function is continuous at the point x equal to a. Let's see few cases related to this point. Let's consider this case. Here we have a function f of x. The plot is a continuous one. You can see that at the point x equal to a, the function takes a value which is equal to capital L. So this is the point x equal to a. At this point, the value of the function is found to be equal to capital L. Now, if you calculate the limit value at the point x equal to a, if you are getting it equal to L, then we may say that this function is a continuous function. Okay, so when limit x tends to a, f of x is equal to L, and the value of f of x at the point a, that is f of a, if that too is equal to L, then we may say that this function is a continuous function. Okay, so this is the case where we have continuity. From the curve itself, you can see that it's a continuous curve. Okay, so the limit at the point x equal to a, it is found to be equal to capital L, and the value of the function f of x at the point x equal to a is also found to be equal to capital L. So this implies that this function is a continuous function. Okay, let's see another case. In this case, you can see that the curve is almost continuous except at the point x equal to a. At the point x equal to a, function takes a value which is equal to f of a, that is this one. Okay, so when you find limit of this function, limit of the function at x equal to a, it is found to be equal to capital L. The value of the limit of the function at the point x equal to a is found to be equal to capital L. But the value of the function at the point x equal to a, that is f of x at the point x equal to a, which we represent it as f of a, is something different from capital L. Okay, it's not equal to capital L. So this is a case where we have a discontinuity. So we may say that this function f of x, it's not continuous at the point x equal to a, because the limit value is different from that of the value of the function at the point x equal to a. So f of a is not equal to capital L, that is limit value at the point x equal to a. Therefore, this function is a discontinuous one. Okay. Now let's see another case. In this case, you can see that the function is clearly discontinuous at the point x equal to a. It is defined up to the point x equal to a minus. Okay, it is defined up to the point x equal to a minus, and also it is defined from the point a plus towards infinity. Okay, but it is not defined at the point x equal to a. We have a discontinuity here. So when you see the limit, you can see that limit does not exist in this case. Okay, So it means that f of x is not continuous at x equal to a. Now let's see few practice problems. Problem number 1. Find continuity of the function f of x equal to mod x at the point x equal to 0. So here we are asked to find out whether the function f of x is continuous or not at the point x equal to 0. So to find that, at first we have to see the definition of f of x. F of x is nothing but mod x. Okay, and how this function is defined? Its value will be equal to x for all x values greater than 0, and this function will take values equal to minus x for all x values less than or equal to 0. Okay, so this is how f of x is defined. Okay, now let's see what is the value of the limit as we approach the point x equal to 0 from the right side. That is, limit x tends to 0 plus f of x. Okay, so this will be equal to limit x tends to 0. F of x is taking the value equal to x for all x values greater than 0. Therefore, for x values greater than 0 or for x equal to 0 plus, f of x is defined as x itself. So let's replace f of x with x. So we may rewrite this expression as limit x tends to 0 x. Okay, now when you substitute x equal to 0 here, what we get is 0. Okay, so the limit value of the function f of x at the point x equal to 0, when we approach the point x equal to 0 from the right side, it is found to be equal to 0. Okay, now let's find out the value of the limit when we approach the function f of x from the left side. Okay, so let's find out limit x tends to 0 minus f of x. What we get is limit x tends to 0. F of x will take values equal to minus x when x is less than 0. Okay, so for all values less than 0 minus and including 0 minus, f of x is found to be equal to minus x. As per this definition, f of x is equal to minus x for all x values less than 0. Okay, so let's replace f of x with minus x here. So we may rewrite this left hand side as limit x tends to 0 of minus x. Okay, now when you substitute x equal to 0 here, we get the limit value. We get it as minus 0, and that is equal to 0 itself. Okay, so here limit x tends to 0 plus f of x and limit x tends to 0 minus f of x are found to be the same. That is, both are equal to 0. Therefore, limit exists at the point x equal to 0. Now let's find out what is the value of the function f of x at the point x equal to 0. Okay, so the value of the function f of x at the point x equal to 0. Okay, that is equal to, you can check the condition at x equal to 0. Here f of x is defined as minus of x at the point x equal to 0. Okay, so therefore it is equal to minus of 0. As per this definition, f of x at x equal to 0 will be equal to minus of 0, and we are getting it as 0. Okay, so the conclusion is that we are getting limit x tends to 0 plus f of x equal to limit x tends to 0 minus f of x equal to f of 0. Okay, so this implies that the function is continuous at the point x equal to 0. So from this we can make the conclusion that f of x is continuous at the point x equal to 0. Okay, now let's move on to problem number 2. Problem number 2, check continuity of the function given below at x equal to 0. So here the function is defined as f of x equal to x cube plus 3 for x not equal to 0, and f of x is equal to 1 for x equal to 0. So here let's calculate limit of the function at the point x equal to 0. So limit x tends to 0 f of x is equal to limit x tends to 0 x cube plus 3. Okay, so for all values other than x equal to 0, function is defined as x cube plus 3. So f of x will be equal to x cube plus 3 for x tends to 0 plus as well as x tends to 0 minus. Okay, so we need not find out limits separately. We can straight away find out the limit at the point x equal to 0 by substituting f of x equal to x cube plus 3. Okay, now this value will be equal to 0 cube plus 3. So we will get it as 3. So the value of the limit of the function f of x at the point x equal to 0 is found to be equal to 3. Okay, now let's find out the value of function at the point x equal to 0. That is f of x at x equal to 0. Okay, let's denote it as f of 0. Okay, so value of the function at the point x equal to 0 is defined as 1. Okay, as per the definition of f of x, its value will be equal to 1 at the point x equal to 0. Therefore, f of 0 will be equal to 1. Okay, now when you compare these two results, you can see that limit x tends to 0 f of x is not equal to f of 0. Okay, so from these two we can conclude that limit of the function f of x is not equal to the value of the function at the point x equal to 0. So this implies that the function is discontinuous. Okay, the function is not continuous at the point x equal to 0. So function f of x is not continuous at the point x equal to 0. Okay, so that's the result. Now let's see problem number 3. Check the continuity of the function at x equal to 2. So function is defined as f of x is equal to x cube minus 3 for x values less than or equal to 2, and f of x is equal to x square plus 1 for x values greater than 2. Okay, so let's calculate the limit value here. Limit x tends to 2 minus f of x. It will be equal to limit x tends to 2. F of x is defined for x values less than 2 as x cube minus 3. Okay, for all x values less than 2, f of x is defined as x cube minus 3. So let's substitute this expression here. So what we get is limit x tends to 2 x cube minus 3. Okay, now here let's substitute x equal to 2. So what we get is 2 raised to 3 minus 3. So that is 8 minus 3. We get the answer as 5. Okay, now let's calculate limit x tends to 2 plus f of x. X tends to 2 plus f of x. So the function value or the expression of the function for x greater than 2 is defined as x square plus 1. So f of x is equal to x square plus 1 when x is greater than 2. So let's rewrite this one as limit x tends to 2 x square plus 1. Okay, now substitute x equal to 2 here. What we get is 2 raised to 2 plus 1. Okay, so that is 4 plus 1. We get the answer as 5. Okay, so this implies that the limit of the function at the point x equal to 2 will be equal to 5. Okay, so we have calculated the limit value for the function f of x at the point x equal to 2, and we are getting it as 5. Okay, now let's calculate the value of the function f of x at the point x equal to 2. Okay, so it is denoted as f of 2. When you substitute x equal to 2 in the expression of f of x for the point x equal to 2, what we get is 2 raised to 3 minus 3. Okay, for x equal to 2, f of x is defined as x cube minus 3. Okay, so f of 2 will be equal to 2 raised to 3 minus 3. So that is 8 minus 3 and we get the value as 5. Okay, so from these two we may conclude that limit value for the function f of x at the point x equal to 2 is equal to the value of the function at the point x equal to 2, that is f of 2. So limit x tends to 2, f of x is equal to f of 2. So this implies that the function f of x is continuous at the point x equal to 2. Okay, so that's the answer. F of x is continuous at x equal to 2. Okay, so with this we are coming to end of lecture 20. In lecture 20 we discussed about continuity of a function at a given point. So for a function f of x to be continuous at a point x equal to a, it has to satisfy this condition, that is the limit value of the function at the point x equal to a should be equal to the value of the function at x equal to a. Okay, so if this condition is satisfied, we may say that the function is continuous at the point x equal to a. In lecture 21 we will discuss about derivative of a function. So see you in lecture 21. Goodbye.